So now we go to sequence motif finding. When we started this is like scary, over 20 years ago, there were not many known transcription factor motifs. It was a very small collection. So de novo motif just means assume we know nothing about transcription factor motifs. Let's just start looking blindly. The goal is, if we're given the inputs data, for example, genes whose promoters, promoter of genes that form an expression cluster, so the lights that are on and off together, right? So we were looking for the common light switch between them. So we're trying to look for a sequence pattern. And depending on the different way of representing the motif, there are two different major classes of motif finding approaches. If you have a regular expression, and in order to look for that motif enrichment, it's called a pattern-driven approach. The idea is, most of the time, unfortunately, we don't know how long the motif needs to be. You just have to make some intelligent guesses. You try like 6 or 9 or 12 or 15, and you see which one gives you a better result. So with regular expressions, and we call this k-mers, you are looking for enriched k-mers, and you want to check whether they are significant in the data set. So the idea is we try every possible k-mer. Let's just say, this is a W-mer. That W is a width, or k-mer is the same idea. You're looking for, let's say, a motif of width 9, and you're just trying all the possible 9-mers, because every nucleotide, it can be either A, C, or G, or T. The next nucleotide, it could be A, C, G, T. And so you look at all the possible 9-mers, and you ask, okay, let's look at the genome. How many times does this particular 9-mer appear in the genome background? And if my input data is a portion of that, how much do I expect to see? And then you ask, in my promoter, like a group of input sequences, how many times this particular 9-mer appears? And you ask whether this is a significant enrichment. It's like coin flip, right? If the likelihood of each coin flip is 50%, what's the chance that you did 200 coins and you get 180 heads or something like that, right? So you can calculate some enrichment for that. And so basically, if this particular k-mer appeared X number of times in the genome and your input size is this big, if you observe that the k-mer occurrence is much, much higher than expected, that's an enrichment. And you just try all the possible k-mers and see whether they are enriched. Pretty standard approach, right? The method is very exhaustive because you have really tried everything. It's guaranteed to find the computational global optimum. Because you really try everything. And you can also find multiple motifs, because you've tested all the possible 9-mers. However, using this approach is not as flexible with base substitutions. Even if you were to use the generate motif, use the IU pack, you say, okay, this base can be either A or C, it's not very good. And also, sometimes they give you a very long list of motifs, and you look at them, they all look very similar. Most of the time when biologists run an algorithm, they hope to see 5 or 10. But when you give them a list of 300, they get really confused. So it's hard. And also with this approach, we are more or less limited with motif width, because by the time you have a 15-mer motif, you have to enumerate 4 to the 15th, which is very hard. And when you look at your sequences, it could be that nothing has a perfect match. Even your motif is there, but they all have a little bit of mismatch here and there. Then you will not have a hit. Right? But still, over the years, I think people are improving on this, and there's an algorithm called Weeder. You can click on this and go to the link. They use a suffix tree implementation. Basically, they can just enumerate, because your input sequence could be long, and they can look for hits very quickly and see which ones are enriched in the data. So that's regular expression. But then remember, the second way of representing the motif is using the position weight matrix, using this probability matrix to represent the motif. When you are trying to look for, de novo, to look for such motifs, using de novo approach, it's called a data-driven approach. The idea is we have no idea where the motif is. We just kind of randomly start somewhere, and hopefully the data will help us find it. There are two quite slightly different methods for this. They both, one is expectation maximization, and the other is called a Gibbs sampler. And they both try to do motif finding. And they actually share the same data model. The idea is like this. We can imagine we have a number of objects. The first is the input sequence. These are the few hundred sequences, each a few hundred nucleotide long. We know that they are enriched for some patterns, and we're trying to look for it, right? And theta 0 is the non-motif, is the genome background. What's the probability of seeing ACGT in the genome? So depending on your genome, I think a human is probably slightly more AT rich than GC. And the theta is the real thing. That's the motif you are trying to find. It's the position weight matrix that you are trying to estimate, the real thing you are trying to find. And then there's also a parameter called pi, which is the motif site location. This is where this motif appears in your input sequences, the location that you keep track of. The problem we are facing is we have the input sequence. We also know the genome background ACGT probability. We are trying to estimate this motif, what does the matrix look like, and also figure out where the motif appears in the genome, where or not in the genome, in your input sequences. We're trying to estimate these two parameters. So let me ask, if you have a motif matrix, are you able to figure out where this motif appears? Supposedly you have some input sequence. You also know the motif matrix. Supposedly we know the motif. Given some input sequence, can you figure out where this motif will appear? You can, right? Because you can use the motif to score each of the small fragments in your input sequence, whichever the higher scoring ones, that's your hit, right? So that's good. If you have a given input sequence and also you know where this motif appears, the hit, we say, oh, this location, that location, this location, you have the locations. Can you know the motif of the transcription factor binding? You can too, because remember, if you have the location, you can just align them together. And then you count in the first base, how many ACGTs do I see? In the second base, how many ACGT I see? Then you can get a probability matrix. Yes, question. Your question is whether they are consensus sequence. You can imagine it as kind of like a consensus sequence, even though some of the bases might be more conserved than other bases. Some base might everybody agree, other bases, different sequences might be different. Okay, yeah, so you can imagine we try to estimate these two parameters together. If we are given one, we can know the other. Unfortunately, when we start, we have neither. We don't have anything. And so it's, so for both expectation maximization and Gibbs sampler, they try to say, okay, let's just start somewhere. We randomly initialize some matrix, for example. And then we try to estimate the pi. And once we know the location of the motif, we estimate the matrix again. And they just iterate. And magically, these algorithms will converge on some enriched motifs, which is hard to imagine, but they did. And so expectation maximization and Gibbs sampler, they both use this approach, except that in their estimation method, they are slightly different. So let's see how expectation maximization works, okay? So in the E step, remember, if we are given a particular, all the input sequences, and this is the genome background, we just randomly initialize our matrix somewhere. It doesn't matter what it is. It can be very weak. You can see here, supposedly this is the initial matrix we give. You can start somewhere. This is base is 70%, 20% T, 10, 1% G. I remember we do not like zeros in the matrix. We give them some numbers, okay? And so now for each of the input sequence, I'm only showing a motif of width 5, but most of time transcription factor binding probably like 8 or 12 or something, right? So I'm only showing you a motif of width 5. And so we look at this particular 5-mer. We say, okay, let's give it a likelihood ratio. Let's score this guy by the current matrix. And we use this likelihood ratio, which is the probability of seeing a T, T, G, A, C in the current matrix, divided by the probability of seeing T, T, G, A, C in the genome background. I'm making it up. Say human genome is 30% A, 30% T, 20% G, and 20% C. Okay, so we're just, So initially, we will calculate a likelihood ratio for this first 5-mer. Then with slide 1, we use this matrix again to calculate the probability of T, G, A, C, G coming from this matrix divided by the probability of T, G, A, C, G in the genome background. Okay, so you can imagine you use the matrix and the genome background to score every little sequence in your input sequence. And each of them are now given a score. This is the expectation step. So expectation is if we know this motif, what are the expected scores that you are going to get for each of the sequences? Then next, we want to do the maximization step, which is now we want to update the motif matrix so that we can maximize the likelihood of seeing these sequences. And so, so now we align all the sequences together. You stack all of the little 5-mers together. And each of them, remember, they have their likelihood ratio score. And now we do a weighted sum of every base to calculate that the new matrix for your motif. So let's look at how this is done. Supposedly this is sequence and this is the likelihood ratio. I'm just making up some numbers, okay? And so we ask, okay, what is the probability of having a T in the first position? There's a T and it got a score of 0.8. Okay, that's here. The next one is T that gets 0.2 score. Okay, we're gonna put 0.2 here. The G's, these we don't have to care. Oh, there's another T that got a 0.9, we'll add it here. And so you can imagine you have many T's in here. Every time you see a T, you use the score in the front to add to the numerator. But the denominator, you just add off all the scores. And that will be the new score you give to your probability matrix of having a T in the first position. Okay, and then for the G in the second position, you ask, okay, well, G in the second position, see here, there is a G in the second position, and that score is 0.2. And then there is another G in the second position, and that score is 0.3. And then you see there's another G in the second position, and that score is 0.9. So every time the G happens on the second position, you consider this score. And the denominator, again, is you add up all the scores. And so then this will give you, on that probability matrix, what is the probability of a G in the second position. And you can start a matrix somewhere, and then you do this maximize. So you'll get the matrix, new matrix. And so using the new matrix, you can do the expectation step again. You use that new matrix to score every word, every little word in your sequence, and give each little word a score. And then you stack all the sequences together, count the ACGTs weighted by the score, you will get a new matrix. And you just iterate. And magically, it will give you the motif. That's how expectation maximization works. Yes, question? So the question is, how sensitive is the method to the window size? if you have a very short window, you will get short words, and they will probably agree very well. But once your word is very long, it's harder to really get everything to agree perfectly. But if your real motif is really longer, it will probably get there faster in some sense. Okay? Yeah, so initially we don't necessarily know which one is better. And at the end, we have to score it. I will show you how to score the motif later. Okay? Yeah, so you can imagine this is, this method is called the expectation maximization because we iteratively do the E step and M step. And eventually it will converge on something. And depends on how you start. You can imagine initially your data might look like, well, so you can imagine your motif is kind of there are some enriched hidden signals in your data, and you're trying to use EM to identify it. And there might be more than one motifs, and in a kind of motif, this is a landscape of the real like a motif. So supposedly these are all the possible motifs, and they are relative enrichment in the genome, or in your input sequence follow some kind of a distribution. This is the kind of the, so you look at all the possible different motifs, their enrichment pattern might be slightly different in your data. For expectation maximization, it depends on where you start. So supposedly you start in here, there is only one way to converge because the E and M step is very deterministic. If you start from here, it will converge to this place. Then you will say, okay, that's it, that's the end. At that time, you will see that, so when you run this EM algorithm, initially you start from a very weak motif. But as each iteration, you can see this matrix change, but it's changing smaller and smaller. When does it converge? It's when from one round to the next round, the matrix almost don't change anymore. That's when the matrix converged. And very often, if you start, so if you start your initialization from here, eventually it will kind of plateau, it will reach here, it will stop. But if you initialize your motif in here, it will converge to here for sure. And if you start from here, it will converge to this. And so it is kind of a greedy hill climbing approach to find the local best, wherever you start, you will find the local best enrichment for this. And so hopefully you start with something that's promising. And so in this algorithm that's still publicly available and maintained by UC San Diego Supercomputer Center and also scientists in Australia, Tim Bailey, they do something like this. Given the input sequence, your input is a few hundred bases, and each of a few hundred sequences long, they try each of the k-mer as in your input sequence as the motif matrix. So you can imagine a very simple way is if I'm using this word to create a motif matrix, what I can do is I want the first T to have, say, maybe 70%. And then the ACG in that first position will only give 10%. And the second T, this is the first position. And the second position and the T is 70%, ACG is 10%. And the third position, because it's a G, I'm gonna give the G 70%, each remaining one 10%. So you can use each of the word in your input sequence to create the initial matrix, the initial probability matrix. And then you can use your input data to run it. Just one round of EM, and you can see whether it looks promising or not. If it's promising, so basically the MEME algorithm use every input sequence to initialize a matrix, and then they only run one round of EM. Then they ask which one is promising, then they take the top 100 promising ones to run till convergence. So you can imagine on this landscape, they just kind of randomly start. Basically, you can imagine they randomly start all the places and let them run with one iteration of EM. So we use one iteration, each of them go up one step, right? If you start from here, it go up one step. If it starts there, it go up 1 step. And then at that point, it just take the highest scoring 100 and allow them to keep running until convergence. And then they will compare the score again and report to maybe the top 10. Okay, so that's how it's done. And it actually works quite well. And that's the EM algorithm. I'll tell you later why these type of algorithms converge. Basically, you start somewhere. You say, okay, I'm trying to find the things that are enriched in my data. And because you randomly start somewhere, it will try to score each of your input sequence. And supposedly, even if you were to start, let's just think about this case. If initially you have 25% ACGT of everything, then each of these will be the same score, right? Because initially your matrix has no enrichment. You start from completely random. If you were to start at 25% of ACGT, and now you add all the scores together, you'll stack them up, what's going to happen in that case? The k-mers that appeared more times in your data, there will just be more entries to add. Does that make sense? Because if your matrix initially is 25% of everything, it will have no preference. All of the k-mers will have the same score initially. But then when you stack them together, the k-mers that appear more often in your data, there are just that many entries in the data, then they will together skew the matrix towards the correct enrichment you're trying to look at. Because, if there is indeed an enrichment of TTGAC, there are more TTGACs in your data, and you have just more T's in that first position, and more T's in the second position, and more G's in the third position. Does that make sense? That's a simple way of thinking about it. So you are doing kind of a weighted average of all the sequences in some sense. And then whatever k-mer is enriched in your data will eventually show up. Okay, so that's kind of how the EM algorithm work.